feedback control. It's the unsung hero of all modern technology. Imagine a world with no commercial aviation, because even though modern airplanes are incredible feats of engineering, there aren't any control systems to drive the behavior of the control surfaces. Imagine a world with no modern computers, because there isn't a control system to do precision positioning of the hard drive read head. Imagine a world with no turn-by-turn directions, because GPS navigation can't exist without feedback control. Imagine a world with no Amazon Prime, because there isn't a control system capable of managing the thousands of robots in each football field-sized fulfillment center around the country. This is a world without feedback control. And while I might be overstating things slightly, the fact of the matter is that feedback control systems are an essential part of all, and I mean all, modern technology. In this class, we're going to learn the fundamentals of feedback control systems, and we're going to learn how to do analysis and design of some essential control algorithms and see their application to real-life systems. So, without further ado, let's get into it. It all pretty much starts here with the Unity feedback control system. This is a block diagram that governs most of modern control systems and is a good place for us to start. If we take a lap around this feedback control system, we can try to identify all of the major components. The block with a P inside of it, this represents the plant. This is essentially the dynamic system that your feedback system is going to try to control. So this could represent a vehicle, it could represent a robot, it could represent a temperature control system. Really, it could be anything with dynamic behavior that we can use feedback control systems to control. Why? This is the measured output. This is the actual variable that you are trying to control. And the way that our computer systems are going to measure that output is through some type of sensor. We'll go into some examples once we get through this general outline, but all systems need some type of sensor to measure their surrounding parameters. Continuing on, the R signal, this is called the reference. This is basically the signal that we want. So if you imagine, and we're going to come back to this example quite often, if you imagine a cruise control system where you're cruising down the highway, you're getting a little bit tired, so you hit cruise control so that the vehicle will maintain the speed for you. The reference here is the speed that you want the vehicle to go. Okay, so if you're cruising at 65 miles an hour, as soon as you hit on for the for the cruise control system, you have specified the reference. And now it's the cruise control system control job to maintain the measured output at that desired reference. Okay? Which brings us to the next signal. Looking at this block diagram, you can probably figure out that E is the difference between R and Y. So E itself is called the error signal, and it's actually just the difference between R and Y. Now this is a really important signal because the error itself is kind of the key to the whole feedback control structure working. The reason is the error contains information about both what you want and what you currently have in real life. So embedded within the error signal is all of the information that the control system needs in order to generate the proper actuation. Okay? Notice now that the error signal becomes the input to the C block. The C block is called the controller, and this is what we're going to spend most of this class learning how to design, is what goes into this block here. Okay, so the controller is actually not a physical device. It's actually just an algorithm. It's a transfer function. It's basically itself a dynamic system which you design to process the error signal, and the output of the controller is going to be U, which is the control command. The control command is the output of the controller, but if you look on the block diagram, it becomes the input to the plant itself via some actuator. Actuators can take many forms. Some common actuators in robotics are DC motors, or linear actuators, or engines, or any other type of mechanism that can translate the control command U into actual physical forces. And with that, we sort of end up back at the starting point of this loop, which is the input to the plant itself. Okay, so this is the most general outline for how this feedback control system works, and we're going to leave it in this really general format because this particular Unity feedback control structure is so versatile, it actually applies to thousands and thousands of different types of control systems. Okay, so we kind of have to leave it in this general form so that as we apply it to individual systems, you can see how each component is going to correspond to that particular system. Okay. The idea here, okay, the main idea here is that that same feedback control system can apply to many, many different types of systems. Okay, so I'll just sketch out a few here to give you a sense for how versatile that block diagram actually is. Okay, so let's start with one of the first examples that I mentioned earlier. Wonder what this is. Okay, so I'm testing my artistic abilities here. This is a hard disk drive out of a modern computer system. If you have solid state, great for you, but there are a lot of computers that still benefit from the and it's strange to say, the old-fashioned hard disk drive where there's an actual disk with information on it that's spinning really fast. Okay, in order to do anything on a computer with this type of hard drive, whether it's to retrieve a picture or open some type of document, you actually have to position that read head very precisely. Okay, and the only way to do that is through feedback control. Okay, so one way to sort of very simply outline this type of system is to define the measured output, which again is that Y signal. This is basically the actual, and we can just say, and we're really simplifying this here, we can say it's the angular position of that spinning hard disk drive. Okay, but let's suppose you want to open a particular document. What that means is you're really saying, well, I need to go to a very specific location on that disk, which means I'm going to set some desired position as my reference. Okay, so then from there, it's basically the control system's job to position that disk to a very specific location. Okay, so the control effort required in this system comes from the motor torque. Which is supplied inside of the hard disk drive itself. Okay, so there's some motor torque that's being applied to position that disk to a very specific location. Now I understand this is a very simplified view of the hard disk drive. More likely it's the angle of, or it's the position of the read and write head that you're actually controlling, but the same concept applies here. Okay, let's look at another example. So this right here, well, didn't draw that very well. This right here is your Segway scooter. Okay, the two-wheeled balancing scooter that's sort of like an inverted pendulum, which fundamentally is all a Segway scooter is. It's an inverted pendulum with a control system that allows you to take advantage of the unstable dynamics to drive yourself around. Okay, for the Segway scooter, the parameters are largely the same as the hard disk drive example that we just looked at. Okay, for the Segway scooter, what you want is basically to remain balanced, right? You want to not fall down even though you're only supported from two wheels at the bottom. Okay, so for just the balancing portion of the Segway scooter, what you have is basically, as your measurement, it's the angle from the vertical, right? Right? The angle measured from the vertical, if you were sort of draw a line straight up through the Segway, the angle measured from the vertical is your actual measurement for this control system. The desired position, if you want to be a self-balancing Segway, is basically 0 degrees, right? You want to be 0 degrees from the vertical, and that constitutes that the system is self-balancing. So your reference is actually 0 degrees. And through the feedback loop, it's going to constantly be monitoring the current angle from the vertical and comparing it to that reference. And based on whatever the error is, the controller block itself will send out a control command, which is again just going to be a motor torque to the wheels at the bottom, right? So if you start leaning forward, the control system is going to say, oh, we're leaning forward, you better drive those wheels forward to counterbalance that error signal. Okay, try to bring that error back down to 0. Here's another one. Okay, this is a this is an HVAC system. Stands for heating, ventilation, and air conditioning. All modern buildings, whether it's a office building or hospital or grocery store or a university, they have control systems built in to maintain the temperature of the room and the space. Okay, basically it will continually monitor the temperature, right? If you notice on the wall of most buildings, if you walk in, you can always find it somewhere. There's like a little box on the wall, and that's the thermostat. So I'm sure you're all familiar with the thermostat. The thermostat serves a couple of purposes. There's a sensor in the thermostat that's constantly measuring the current temperature in the space, so that's where we're going to get our measurement. But there's also a couple of buttons usually on the thermostat where you can go and set the desired temperature. Okay, so if it's a summer day and hey, it's pretty hot outside, it's getting warm inside too, we better set the air conditioning to 74, 75, depending on your preference. Okay, so the reference, that's your desired temperature. And then again, the system is going to constantly monitor the measured temperature versus the desired temperature. And if the difference between the two, in other words, if the error gets too large, the controller will do something about it. And in the case of an HVAC system, the actuator is generally a fan that blows. There's generally two ways that a HVAC system works, right? So if it's warm and you want to cool the space down, you're either going to blow a larger volume of air into the space, of cooler air into the space, or you're going to maintain the volume flow rate of air in, but you're going to cool it down using some type of cooling coil. So there's a couple of different ways to do that. Ultimately, through a damper or some, a VAV or some type of variable frequency drive, you can control the speed of the fan, or you can do some type of cooling coil valve, right? So those are your actuation options for an HVAC system. The point here is that, again, this all falls under that same unity feedback control structure. So any one of these three systems can be controlled by unity feedback. Okay, let's just look at one more because this is an example that we're going to use quite often. Just put it here so that it's all in one place. Okay, so you have basically a vehicle. You have vehicle dynamics, that's your plant, right? That's the dynamic system that we're trying to control. Now for cruise control, we are basically just implementing a unity feedback control system to do the velocity component of the driving for us. Okay, you still have to steer in most vehicles unless you've got a self-driving car. But most of us don't at this point. But most cars do have a cruise control feature where you can let the control system drive the velocity for you. Okay, so in the cruise control example, the measured output it's not an angular measurement, it's not a temperature measurement, it's actually a speed measurement. So it's basically theta dot, right? It's another way to look at it is that it's the angular velocity, right? So really what's happening is the vehicle is measuring basically how fast the tires are rotating, and from that it's computing the vehicle speed. So this is your actual speed, and we'll just call that v, which is the vehicle's velocity, at that point. And then when you set the cruise control system to go, what you're basically doing is setting the desired speed. Right? So you're setting the reference signal when you push the cruise control on button. And then you can let your foot off the gas, and you notice that the car will, depending on the outside conditions, it will sometimes go a little bit faster or a little bit slower, but it'll always try and maintain that desired set point speed that you had specified. And the way that it does it is through the control command sent to the actuator, which is in this case the engine. Right? So it basically throttles the engine automatically so that you maintain the desired speed. Okay? So, I mean, I could go on all day with these types of examples, but the whole point again is that this unity feedback block diagram, this structure is so versatile that it makes sense to study this particular control system because it applies to so many different types of control systems, as we've seen here. Okay, so I'm just going to do one more example, and you might feel that it's overkill at this point. If you're starting to understand the concept of the feedback control loop, that's great, but I just want to throw out one more example, in part because it's fun for me to do, but also because it sort of is a nice segue into the next point that I want to make. Okay, so for this example, what I'm doing is basically, let's see if I can draw this here. I am supporting a stick, some type of long, slender, rod. In this case, I'm just using a wooden dowel. And what I'm trying to do is balance that, right? So this is, for all intents and purposes, this is basically the same dynamical system as a Segway scooter. It's an inverted pendulum, which means that it's a vertically supported structure supported from the bottom in a gravitational field trying to pull it down. Right? So all that put together makes this an unstable system. And what I want to do with you guys, well, I can't do this really live, but what I want to do now is try to identify all of the same components in the feedback structure, right? To really emphasize that the same feedback structure can be applied even into this, what I'm going to call biomechanical example. Bio being sort of the human component, and the mechanical being the sort of inverted pendulum dynamics. Okay, so as we go through, we'll try and sort of identify all of these parameters in the traditional unity feedback control structure. So here it is again, just for your reference. There's your actuator, plant, sensor, and then back to feedback. Okay, so notice the first thing is we can demonstrate that this is actually an unstable system. And the way you can tell that it's an unstable system is that if you do nothing, well, the output diverges, right? The angle from the vertical, in this case, the output of this system is the angle measured from the vertical. Notice that if I do nothing, the stick just falls down. In other words, theta diverges. It doesn't go to zero, it actually approaches infinity. And it won't actually approach infinity. All that happens is that it falls down, right? So the stick falls down. This is an unstable plant, but the plant itself in this system is the stick, right? But it's also the configuration that it's in. the fact that it's supported from the base in a gravitational field trying to pull it down. Um, and that's basically it. So the inverted pendulum dynamics, that is the plant, right? That's the system that we're trying to control here. The measured output, that's the actual angle from the vertical, right? That's the angle measured from the vertical. And we'll call that theta, right? That's the actual deviation from the balanced point. Okay. Now, if I am trying to close the loop on this unstable system and stabilize it, what I'm trying to do is set a reference angle of 0 degrees. In other words, I want to balance it, but what that means mathematically is I always want theta to equal 0 or as close to 0 as possible. Okay. The sensor in this system, well, the sensor is the visual feedback that I'm getting by looking at the stick. Okay, so this is sort of the bio part, the biological part. Right? So the sensor is the visual feedback from the eyes, right? Okay, so I'm looking at the stick as it's balancing, and I'm saying, uh-oh, it appears to be off, right? But the sensor itself can't do anything to correct that imbalance, right? The sensor is just giving information to the controller. And in this case, the controller is actually the brain, right? So the controller is basically accepting the error signal, right? So the error signal is the input to the controller. And the error signal, again, remember, is the difference between R and Y, right? So it's R minus Y. I know that R is 0 degrees. I want this thing to be balanced. And I only get the Y measurement through the sensor, right? So that visual feedback is what allows the error signal to be constructed. The error signal is then processed by the controller, which in this case is the brain, and the brain will then send control command to the actuator. The actuator in this case is the arm, right, or the hand, or basically it's all of this stuff that allows me to manipulate the position of the base of that stick so that I can counteract any imbalances. Okay, so the actuator slash control command, the control command is basically the movement of the arm and the hand so that I can try to maintain the balanced state. Okay, and then when we put it all together, if the control is good, right? If the controller knows what to do with the information that is being processed, and if the actuator is fast enough and precise enough, then we can produce a balanced state. Okay, so this is the last example that I'll do for this lecture. Again, remember the whole idea here is that this single unity feedback control structure is very versatile, and it applies to so many different scenarios that it's kind of the starting point for our discussion of feedback control. Okay, the thing that I want to highlight about this example is, well, what happens now? What happens if well, actually, let me do this. Let me pose the question of why use feedback control at all? What is the point of using feedback control? One of the primary uses of feedback control is that it can stabilize unstable systems. That's something that only feedback control systems are capable of doing, is to stabilize an unstable system. So what we have here is a plant, right? A dynamic system that is inherently unstable. Right? The inverted pendulum system is an unstable system, and yet we are able to demonstrate that through feedback control we can stabilize it. Right? So this is kind of a silly example of balancing a stick, but it applies, like the same concept applies to many of the unstable systems that exist in everyday life. Okay, so the question that I really want to pose to you is, well, what happens if we don't use feedback? Is there any way to maintain that balanced state of the unstable system without feedback? And the way to check, well, is to eliminate the feedback path, right? So if there is no feedback path, then what happens? And the way I can eliminate the feedback path here is to basically cut the sensor, right? If I eliminate the sensor, then everything downstream of this input will also be eliminated, and therefore I will have no feedback path anymore. The way that I can eliminate the sensor in this example, well, all I have to do is to close my eyes. Right? So once I close my eyes, I've basically eliminated the feedback path, and I'm running what's called open loop as opposed to closed loop. Now see what happens if I try to balance this stick in an open loop configuration. It's simply impossible. It can't be done. Okay, so all of this is essentially to illustrate the idea of two classes of control systems. Okay, so there are a class of systems that use open loop control. And open loop control basically looks like this. You've got a control system and you've got the plant, and it just goes straight through. There's no error signal, there's no monitoring of the current state of the system. It's just here's what I want. I really hope I get what I want. That's what an open loop control system is doing. Now there are situations where open loop control works, and it's actually a great scenario because it's very simple to use open loop control. Okay, the only things, there are a couple of caveats here. Open loop control, it simply can't stabilize unstable systems. It's impossible for an open loop control system to reliably stabilize an unstable plant. For that reason, because there's no feedback coming back to the controller, fundamentally guessing is the only option. Now, I'm not saying that in any type of negative tone, like guessing is the only way that you successfully implement open loop control. There are some scenarios where if you know enough about the system, then open loop control is fine because if you know enough about the dynamics of the plant and you know enough about how the control system is going to influence the plant, then everything will be fine. For example, let's look at this. Let's look at this common household appliance. This is a toaster. This is a toaster. Yeah. I can't spell toast. This is a toaster. It's a device that turns bread into crispy toast. Okay, so basically what you have is you got a piece of bread that you put into the toaster, and you turn the dial to apply some heat, and what you get is nice crispy toast, right? Now, how is this an example of an open loop control system? Well, the plant has some dynamics, right? It applies heat at a certain rate, and that heat will interact with the bread and sort of toast it. If you apply too much heat, it gets burnt. If you apply not enough heat, it never becomes toast. It just stays bread, right? So the controller here is how much heat you're applying, and the plant itself is the the properties of that particular piece of bread. Okay, so I happen to know that for the brand of bread that I buy and for my particular toaster, if I turn the knob approximately pi over 2, about 90 degrees, I can basically get perfect toast every time. Right? There's no feedback involved to continuously monitor the state of that toast. It just, I know what I want. My reference is nice, crispy toast. I know that if I apply a certain input, right, turning the knob to a certain point every time, I know that I will get the desired level of toast. I can't believe I'm going to publish this lecture to the world, and we're talking about toast in a senior level control class. That's okay. That's whatever. That's what I do in real life, so I'm going to do it here on the recording as well. Sorry. Okay, here's the thing though. The reason this is a good example is because open loop control, like I said, is only good if you know pretty much everything about that particular system. In other words, well, what if I were to buy a different brand of bread? Now everything's different. The toasting properties of that particular brand may be different. The dynamic behavior might change. Or what if I decide that, hey, this bread is going to start to go bad pretty soon, let me throw it in the freezer. If I throw a frozen piece of bread into the same toaster and turn the knob to the same input, there's no way that I would expect to have the same level of toast in the output. Okay, so as silly as this example is, I believe it illustrates the limitations of open loop control. Okay, so there's your open loop control, and I'm only bringing this up basically to say that we're not going to study open loop control in this class. I just want you to know that there are these two classifications of control. What we're going to spend all of our time analyzing in this class is closed loop control systems. Now this is basically what we've already been discussing. For closed loop control, you've got your controller in your plant, but you also have a feedback path. And that feedback path is key because it's the one ingredient that is allowing the error signal to, like I said before, contain information both about what we want, which is R, and what we actually have in real life, which is Y. Right? So that one little difference there is what makes all the difference in the the closed loop control diagram. Okay. What we've already learned is that closed loop control can stabilize unstable plants. And that's pretty huge. There are a lot of unstable systems that require closed loop feedback in order to stabilize. Okay? But more than just stabilizing unstable plants, it can actually improve the performance of already stable systems. Right? You can get more precise control. You can get better. You can actually shape the output essentially however you'd like of a system that's already unstable by using feedback control. Performance, that's kind of one of those hand wavy. I haven't defined what performance means, and we're gonna get into that throughout the course of this series. But performance can be, it can have to do with stability, right? Is the system stable or not? And I'm talking about the closed loop. I'm talking about the closed loop system. We can talk about robustness as a performance metric. We can also talk about speed of response too. Right, so all of these are sort of general performance metrics that we can basically fine-tune the controller to sort of focus on any one or more of those performance metrics. Okay, so this is your sort of discussion of open loop versus closed loop control. This is where we're going to be spending all of our time, but you need to be aware that there is such thing as open loop control, and you also need to be aware of when it's appropriate and when it's not. Okay, so what we have to do, okay, I know I've set up a lot of the sort of foundation for this class. I've tried to give you a roadmap of what feedback control is used for, first of all, and sort of the benefits of using feedback control to control dynamic systems. Unfortunately, we can't just jump straight into the control design strategies just yet. I need to be absolutely certain that we understand what the dynamic behavior of a system means before we can actually close the loop around it. So what I'm basically asking is, do we understand enough about the actual plant that we're trying to control? Because if we don't, it's a little bit jumping ahead to try and do feedback control if we don't exactly understand the dynamics of the open loop plant by itself. Okay, so most of you should have taken some type of dynamic systems course already as a prerequisite to this course. And in that class, you should have learned about dynamic systems. You should have learned about dynamical behavior of particular dynamic systems. And what that means is, first of all, do you understand the difference between a static system versus a dynamic system? Because a static system really has no need for feedback control. It's the dynamic system behavior that can be interesting enough to warrant using feedback control. Okay, so we really need to understand basically what is the plant all about, right? So this is we're stepping back a little bit here. We're pumping the brakes a little bit. We're not going to jump right into control design strategies yet, because we need to make sure that we understand exactly what's going on with this plant before we try and wrap a feedback loop around it. Okay, so the plant itself represents some type of dynamic system. Right, so I basically introduced a new term here that I need to define. The plant is a dynamic system. Now, I know you took a course on dynamic systems, but it may be the case that the emphasis of that course was different and maybe not alluding to the subsequent feedback control system course that you were going to take. So I'm going to do a little bit of a review here on what a dynamic system is. But as I do this, I'm definitely going to be tailoring this review towards the eventual use of feedback control. Okay. At its heart, a dynamic system is the following. Okay, so this is your fundamental definition of a dynamic system. And I understand that it's vague and sort of wordy, but it really has to be this way because dynamic systems come in all different flavors: mechanical, electrical, biological, economical, geographical. Any type of dynamic system you can think of fundamentally falls under this definition. And it's basically just an input-output relationship, but it's specific in that the present output at time t is dependent on the present input and past inputs. That's the key difference between dynamic systems and static systems. Okay, in other words, dynamic systems have somewhat of a memory associated with it, right? The current output at time t is dependent on a whole bunch of past inputs, right? That's what I mean by memory, right? Let's take this example as sort of a hopefully relatable example. The bicycle. Okay, so this should be a very familiar, hopefully relatable example of riding a bicycle. Okay, so in a bicycle, you turn the cranks, which is your input. Right, so you turn the cranks spin a chain. The cranks are basically a pulley attached to a cog on the back, which is attached to the wheel, which spins and gives you forward motion. Right, so the output of the bicycle system is the forward velocity that you get by turning the cranks, and the input is your torque applied to the cranks. Okay, the bike system has some mass associated with it. It's in our Earth's atmosphere, so there's some aerodynamic drag associated with it. All of that factors into the dynamic behavior of this system. However, what we're trying to do is define why is this a dynamic system? How does this definition fit in with the bicycle system? Well, let's think about the current output, right? The current output is the velocity at time t, right? This is the current output here. Current output. This is equal to, well, it's definitely a function of the current input, right? Are you pedaling at this very instant in time? If you are, of course, that's going to factor into your current velocity. But you can also imagine a scenario where you're coasting on your bicycle as a result of pedaling some time ago, right? So you don't even have to be pedaling at the current time for you to have some non-zero velocity. In other words, the current output is dependent on the current input, but also maybe some past input, like u of t minus 1 or u of t minus 2, or basically any input all the way back to the start of time for this particular experiment. Okay, so all of this stuff These are past inputs. And we know for certain that your current velocity on a bicycle is dependent on all inputs, current or past. And that's what makes this particular system a dynamic system. Okay? This same concept can be applied to any system as sort of a test to see if it's a dynamic system or not. Okay? If we were to do the following, let's take this example now. And ultimately, this is very similar to the bicycle example, but it's more relatable in a car, I think. Okay, so in a car, what you have is basically your throttle. Right? So you've got the gas pedal here, and here's your foot, and your foot can push down on the gas pedal some amount, right? So some theta. This is your throttle. This is your input. This is controlling the throttle to the engine. So this is the input to the vehicle system. And the output, of course, is the velocity of the vehicle. Okay, so you depress the gas pedal in a vehicle, engine starts turning, all that torque goes to the drivetrain, through the axles to the wheels, your car goes forward. But let me ask you this question. If you are late for something, and we'll call this U of t as the input. If you are late for something and you get into the car and you floor it, you basically just apply maximum input, and this is your input. You basically just say, oh, full gas. What does the output look like? The output, remember, is the vehicle's velocity. Right? So the question here is, what does the output look like? The question that I'm asking is, well, does the output follow the input? Right? Does the output do the same thing as the input? Right? Is that what happens? You floor the gas pedal and instantaneously you're at top speed? No, of course. We know that's not the case. What happens instead is, well, you accelerate. Assuming you start at rest, if you floor the gas pedal, you don't instantly go to your top speed. You start accelerating. Right? If your car is powerful, you accelerate very quickly. And you keep going faster and faster until at some point, assuming you have unlimited road with no stoplights or traffic, eventually something happens. And that something is the amount of aerodynamic drag pushing back on your car is so large that it's equal to the amount of forward thrust provided by your engine. And so you have a net force of 0, so you are no longer accelerating and you reach terminal velocity. Right? So this is basically the fastest that your car can go, and you will remain at that top speed until you release the gas pedal. Right? We know for a fact that this is actually what happens. Right? This is really what happens if you were to get into a car and do that. Now, whether or not you've actually done this test on an unlimited open stretch of road, probably you have not, but you could probably deduce that this is what would happen, just based on your past experience of being in a vehicle. Okay. The point I'm trying to make here is that, well, we already know that this is a dynamic system, right? Because current outputs depend on current and past inputs. The key here is, well, I'm trying to define what it means to say system dynamics. Right? So if you work in this field of dynamic systems and controls and robotics and mechatronics, you often have to do some initial analysis on the particular system you're going to be designing or controlling. And so you're going to get asked questions of, well, what are the system dynamics? How does the system behave? Is it first order, second order, and so forth? The system dynamics fundamentally pertain to how does the input translate to the output? Right? How does all this input force eventually become this output? All of that stuff is housed inside of the system dynamics. Okay? And here's the thing. Your intuition tells you that if you get into a car and you floor it like this, and you just apply full gas, intuitively you kind of know that this is the output that you're going to experience, right? Unfortunately, is just not good enough. Your intuition is not going to suffice when it comes to doing precision control design. In other words, we need a way to go beyond our intuition and actually capture those system dynamics mathematically. Right? We need a way to understand this input-output relationship that is the dynamic system. Okay, so the question is, can we actually capture those system dynamics mathematically? And of course, the answer is yes. Right? If we couldn't do that mathematically, there would be no point to taking this course, right? Yes, the answer is we can capture the dynamics of a system mathematically, and that process is called modeling. Okay, so the modeling process is what allows us to mathematically capture the input-output dynamic relationship. That's what the process of modeling does. And generally, the process of modeling will produce a system of equations that govern the behavior of that particular dynamic system. Okay. So before we jump in, like I said, before we start doing any type of control system design, we need to understand what a dynamic system is. So I've given you a definition now of what is actually a dynamic system, but we also need to be very precise about the system dynamics. So we don't want to just be at the point where we can say, oh, if I get into a car and I floor it, my output is kind of going to go like this. Right? That's not good enough. We need a mathematical means to capture those dynamics before we can move forward. Okay, so one way of doing that is through the process of modeling. Most of the examples we're going to treat in this class are mechanical. They're mechanical systems in nature because this is a mechanical engineering course. However, you should be aware that most engineering disciplines, electrical engineering, computer science, mechanical, mechatronics engineering, they all have a control systems course similar to this, only their systems, their plants are different, right? So we're going to be using mostly mechanical systems, whereas a control course you take in an electrical engineering college might be focused more on electrical dynamic systems, right? So there's dynamic systems of all different types. We're going to be focusing mostly on mechanical systems. And in order to model mechanical systems, one way to generate a model for mechanical systems is to use things like Newton's law. Newton's law, we're going to use Newton's second law exclusively. We're going to use force analysis. So we're going to do a lot of free body diagrams. These are the tools that you're going to use to model mechanical systems. You should just be aware that all of the concepts that we're outlining in this course can be applied to electrical engineering systems as well. It's just that the tools that you're going to use to model electrical systems are different, right? There aren't any Newtonian forces in electrical systems, so to speak. So for electrical systems, you'll use things like circuit analysis and Kirchhoff's current and voltage laws to generate those differential equations. Okay, so just trying to give you some perspective. What we're doing in this class is primarily mechanical systems, but same concepts apply outside of this discipline as well. Let's look at an example. Okay, so let's go back to the same system that we actually just sketched out above, and that's the example of the vehicle. Right, so in the vehicle system, the output is the velocity. The input is basically a forward thrust provided by the engine. And in this case, we're going to consider drag. Aerodynamic drag is non-negligible, right? The only time you can neglect aerodynamic drag is if you're in a vacuum, which is a bit too idealized for our purposes, right? We have to consider aerodynamic drag because it's a real force that we encounter in everyday life. Okay, so we want to model this system, which means we want an equation or a set of equations that describe this system fully so that we do not have to rely on our intuition. Well, it's a mechanical system, so the first thing we want to do is to try and analyze all of the forces in this system. We only care about horizontal forces because we're talking about the horizontal velocity here, so that makes things a little bit easier. There's only one mass involved, and that's the mass of everything that has to do with the vehicle. We can lump into that mass. Okay, there's a force due to the engine. That's our input force, U. And there's also another force. It's the force of aerodynamic drag trying to resist that forward motion. Right? Those are the two forces that are sort of fighting each other in this vehicle system. Okay, the output itself is a velocity, which is it's not a force, it's the output measure, it's the output variable that we're trying to measure. Okay, so the only forces involved are actually the input thrust and the aerodynamic drag. And the aerodynamic drag we're going to model and we're going to approximate as linear, which is not totally accurate, but it's a good first pass. Okay, so basically it's some aerodynamic drag constant times the actual velocity of the vehicle. So you can see that the faster the car is going, the harder the air is going to push back on the vehicle. Right? So this is not a static force. It actually changes as a function of the velocity. Once we've sort of analyzed our forces, then we're going to use Newton's second law, which is basically, you'll remember this from physics, it's F equals ma, right? It's the sum of all the forces in one direction is equal to the mass times the acceleration in that direction. Okay, so if we set a direction for positive here, we'll just do positive to the right. Then we can add up our forces. We have U in the positive direction minus Fd, the drag force, in the negative direction, is equal to the mass times the acceleration. Okay, seems very simple, and it is really. For this simple system, the modeling process is actually quite straightforward. What we have to do, though, is we do have to get away from that sort of high school physics mentality, and we have to jump into a mode of thinking of, well, how does this pertain to the dynamical system behavior? Remember, a dynamic system is an input-output relationship, and so we need to have those inputs and outputs appear in our equations for it to be of any use to us. What I mean by that is, while this equation is technically correct, it doesn't do us a whole lot of good because we've got Fd floating around, we have acceleration floating around. Remember, the input to this system is the forward thrust U, and the output is the velocity. So we want our equation to contain those input-output variables only, with maybe some constants floating around. In other words, what we want to do is replace our drag force with something relating to the velocity. Okay, then we're going to set that equal to the mass, and yes, it's true that it's equal to the acceleration, but again, we want to put things in terms of our inputs and outputs. So the acceleration can also be expressed as the time derivative of the output velocity. Okay, now if we do it this way, what we've basically produced is an ordinary differential equation that only contains the input-output variables and maybe their derivatives, along with some scalar constants. This differential equation is what we want. Okay, and actually what we could do is even to write this in standard form, which is which looks a little bit different, but it's more useful in some respects. Okay, so all I've done here is just sort of solved everything for v dot, which is the acceleration of the vehicle. But what you have here is basically the dynamic system behavior all bundled up into one nice closed form differential equation. Okay, and this is what I mean by capturing the dynamics of the system mathematically. This equation does the same thing as our intuition up here, which is to transform this input to this output, but it does it much more precisely, and it does it in a way that preserves the general nature of that equation. In other words, this equation is not specific to any one type of input, right? So with this equation, we can actually see what the velocity will look like, not just for a constant input, but for any input, right? We can look at sort of an impulse input or like a ramp input, or we can even see what the velocity looks like if we get into a car and apply like a sinusoidal motion to the gas pedal. I don't know why you would ever do that. You know, you're just going to make your passengers sick. But the point I'm trying to make here is that this equation can handle all those types of inputs because it's not particular to any one. Okay, so just to kind of bring this thing full circle, we're now claiming that this differential equation captures all of those vehicle velocity dynamics. Well, let's just test that. Let's just test it for one particular input. For u of t is equal to 1, which is essentially what we drew up there, right? That's just the constant input, right? This represents a constant valued input. What does the output look like? Well, we happen to know that we can solve this differential equation for this nature of an input, and the general solution looks like the following. Right? The general solution looks like v of t is equal to 1 over b minus 1 over b e to the minus b over m t, right? This is the actual solution of this differential equation under the influence of this particular input, right? I kind of just jumped to that answer, but I'm just drawing from your differential equations course. So you already, in theory, know how to solve that differential equation. I'm just showing you what it looks like here, in particular to illustrate what this looks like, right? What does this plot actually look like? Well, when t is equal to 0, right, when t is equal to 0, you have e to the 0, which is 1. So you basically just have 1 over b minus 1 over b, which is 0. So at t is equal to 0, we have a velocity of 0. As t approaches infinity, so e to the minus infinity, that just decays to 0. So this whole exponential decays to 0, and we're just left with a constant 1 over b. So way out at t is equal to infinity, we have a constant value of 1 over b. And in the middle, we basically have a constant value, and from it, we're subtracting this decaying exponential. So what does that look like? Well, it looks like this, right? This is exactly what our intuition said would happen if we got into the car and we floored the gas pedal. Only in this case, an alien that visited our planet who has no intuition for the dynamical behavior of an automobile would still be able to understand that this is the output because we didn't do it based on intuition. We did it all mathematically here. Okay? So this is the power of having a mathematical model for a dynamic system, is that you can essentially you can predict the output based on any known input for that system if you characterize that system accurately. Like if this differential equation is an accurate representation of those system dynamics, well, now you're into basically the idea of simulation, where you can test a bunch of inputs to see what would happen without actually having to go and apply that input to that particular system, right? Okay, this is a concept of modeling. In the lecture notes, which will be posted, there'll be a link to the lecture notes. There are several more examples of basically exactly what we just did. We look at one electrical system just for contrast. We also look at a couple more mechanical systems like the pendulum, with and without drag. And we also look at an inverted pendulum to see that it's got some unstable behavior. And I encourage you to look at those examples on your own time, but fundamentally they're exactly the same as the example that we just did. They just get incrementally more complex. You got a drag force here, you have some additional forces here and there. The concept is identical for those examples. Okay, so I'll leave you to look at those examples on your own. What I want to get to before I end this lecture is, well, where are we going next? Okay, so basically the idea is that, well, okay, having a mathematical model for a dynamic system is great, right? That basically means we can characterize that system, and once we can characterize a system's behavior mathematically, then we can sort of close the loop and do some interesting control design. Only thing is that differential equations exist in the time domain, and differential equations, as you may have experienced, can be a bit tedious to work with. Okay, so in control theory and in many types of these sort of dynamic system analysis courses, we actually opt for a different version of the same mathematical description, and it's called a transfer function. What you should know about the transfer function is that it contains the same information as the differential equation, only it does so in a different domain. It does it in the S domain, okay, the Laplace domain. And so we're not going to get into this yet. This is a topic of our next lecture, but I do want to leave you with this sort of this visual, okay? So you've got over here on the left side, you have the real life system dynamics. Okay, so this is real life over here. And we'll put this in a box that is basically the container for that real life system. This is the actual, I don't know, robotic arm sitting in your lab, or this is your actual vehicle sitting in your driveway, or this is the actual mechatronic system that's going to do some tasks. I don't know. This is your whatever. This is the real life dynamic system that you have. What we just did is we said, okay, well, through the process of modeling, I can generate a mathematical model for those dynamics. And generally, what we get is a differential equation or set of ODEs that describes that particular system. Okay, this version exists in the time domain, but the point that I'm trying to draw here is that these two boxes contain the same information. Okay, one is just a mathematical version of the real life system. To add to this, I'm going to add one more box. And over here is the so-called transfer function. Okay, the transfer function does not exist in the time domain. It actually exists in the Laplace domain, or the S domain, which is a totally different domain, which makes it a little bit less intuitive. But the point I'm trying to make here again is that now all three of these blocks, or all three of these boxes, contain the same information, right? The transfer function is just a different way to represent the ODE, which is just a mathematical way of expressing the real life dynamic systems. Okay? Now, obviously, what I'm getting at here is, well, we need to be versed in all three of these different, basically all three of these different versions of the same dynamic systems. And so to get from the real system to the math model, we use this process of modeling. To get from the mathematical model in the time domain to the transfer function in the S domain, we have to rely on our old buddy, the Laplace transform. Okay, so to get from the time domain to the S domain, you apply the Laplace transform. You can also start from the S domain and jump back into the time domain by using the inverse Laplace transform. Okay, so your very first assignment, actually your very first assignment is going to be can you go back and forth between all three of these different versions of the same dynamical system? So can you model a dynamic system to get an ODE? And then can you generate a transfer function using the Laplace transform? This is all going to boil down, this is all going to be tested in your first assignment. But the idea here is that, of course, the idea here is that all three of these blocks, or sort of containers, they represent the same dynamical system. They represent the exact same input-output relationships, right? Which is again what a dynamic system is. Okay, so we'll stop it here. The next lecture is going to be, well, how do we jump back and forth between the time and the S domain? Admittedly, this next lecture is going to be relatively dry. It's basically just mechanically, mathematically, how do we jump between those two domains? And I'll give you a bunch of examples on how to do that. But because I realize that those are kind of dry topics, I want you to always keep this big picture in mind, right? Ultimately, the tools that you develop and the skills that you develop in being able to go back and forth between all these three different versions is going to ultimately help us to do that really cool control design that we talked about in the first part of this lecture. Okay, so we're going to pick up with basically a review of Laplace transform in the next lecture. and I'll see you there.